So we're going to take a step aside from looking at graphs of exponential functions for now and just look at some rules that involve working with exponents. So for starters, I've given you three tables of values here that I'd like you to complete. There's one for y equals 2 to the x, one for y equals 3 to the x, and one for y equals 2/3 to the power x. So what I want you to do is take some time, complete these tables of values, and then look for some patterns. So you're going to see some patterns as you move down the tables, and I want you to think about what that's going to mean, what happened as you move up the tables as well. So complete the tables, look for patterns, and we'll discuss them when you're finished. Okay, so these are what your tables should look like. I kept everything as fractions because I want to see the patterns that way. I'd like you to keep your exponents as fractions as well. So if you look at these negative exponents here, your calculator might give you decimals. I want them as fractions because you want to be able to see those patterns. And in a lot of cases, you want accuracy as well. You don't want to round anything. So one thing you might notice here, if you look at 2 to the x, we talked about this with the tables of values. In last lesson, some patterns that you might see. The base here is 2, so you'll notice here that as you move up in x values, or down the table here, you see that you're always multiplying by 2 to get from one y value to the next. Okay, it's always going to be multiplied by 2. Okay, so what do you think that means as you move back up the table? Well, if you're multiplying by 2, move down the table here. When you go back up, it'll be division by 2. So here, if you have 3 to the x, you're constantly multiplying by 3 as your x values go up. So if you're going backwards, you're going to be consistently dividing by 3. Okay, with 2/3 to the x, you'll be multiplying by 2/3. Okay, so if you're going back up, you'll be dividing by 2/3, or that would also mean multiplying by 3/2 if you want to look at it that way as well. Okay, so we're going to come back to this when we develop some more rules later on. Okay, but what I want you to do right now is take you back to grade 9. So in the 1D course, you looked at some different exponent laws. And we're going to review them here. So these laws involve working with powers of the same base. So for example, if you have x to the m times x to the n, so you're multiplying two powers with the same base, the rule said that you would then add the exponents. So if you were dividing powers of the same base, you would subtract the exponents. If you had power of a power, so an exponent on top of a power already, you would multiply the exponents. If you had two values multiplied together, all to an exponent, the exponent would distribute. Okay, so you'd wind up, if you're going to distribute the m to both the x and the y, you would have x to the m, y to the m. And similarly, if you had a fraction or division of two things all to the same power or same exponent, you distribute the exponent, you have x to the m over y to the m. So if you remember these rules, great. Remember using them, great. You're comfortable with them, you can move ahead. If you'd like to see how these rules, like where they're derived from, an example of each one, then you can take a look at the last 5 slides in your lesson, starting down here, okay, and it'll go over how we got those rules, where they came from. So if you're comfortable with these, though, if you're comfortable using them, then you can actually skip ahead in the video and your lesson until you get to this slide over here. Okay, but I'm going to take some time now and review where these rules from grade 9 come from. Okay, so for the first law you saw back in grade 9, the product rule. Okay, so let's take a look at an example of 5 to the exponent 3 times 5 to the exponent 4. So if we write this out in expanded form, 5 to the exponent 3 is 5 times 5 times 5. 5 to the exponent 4 is 5 times 5 times 5 times 5. When you multiply those all together, you'll see that now we have 7 5s, so we can simplify that as 5 to the 7. Okay, so using our exponent law, we could actually go straight from here to the final answer by just saying this is the same thing as 5 to the exponent 3 plus 4, which is 5 to the 7. Okay, this would have been the product rule. Okay, so if we look at the, losing my slide here, if we look at the quotient rule, so an example here we could look at would be 7 over 5 times 7 over 2. So again, if you write that out in expanded form, we have 5 7s, so 7 times 7 times 7 times 7 times 7, divided by 2 7s, 7 times 7. And what you'll see happening here is, since we're dividing here, we actually have some 7s that cancel. So 2 7s cancel both the top and bottom of that equation. You wind up with only 3 7s left. Okay, so we can rewrite this as 7 to the exponent of 3. Okay, so the rule of division says that we could actually take a shortcut here, go straight to that final answer by subtracting the two exponents. So you get 7 to the exponent 5 minus 2, which gives 7 to the 3. Okay, so next was the power of a power rule. So here's an example. You have negative 4 all to the exponent 3, then all to the exponent 4. So if something is to the exponent 4, it is multiplied by itself 4 times. Okay, so what we really have is negative 4 cubed multiplied by itself 4 times. So you have 4 copies of those. That's what the exponent 4 is going to do. Okay, and we know that if we have something to the exponent 3, that's just really something multiplied by itself 3 times. So each of these, negative 4 to the exponent 3, gives us 3 copies of negative 4. Okay, so we have 4 copies of that. So we have 3, 6, 9, 12 of them in total. Okay, so you can simplify this as negative 4 all to the exponent 12. So what the power rule tells us, that we can again take the shortcut from here to the final answer by simply multiplying our exponents. So this would be negative 4 all to the exponent of 3 times 4. So we get negative 4 to the exponent 12. Okay. So some other things to remember here. So let's say we had 3x to the exponent 5. Well, again, if something's to the exponent of 5, that means it's multiplied by itself 5 times. Okay, so we get 3x times 3x times 3x times 3x times 3x. 5 copies, because the exponent is 5, of 3 to the x. Okay, so if we multiply those out, okay, so just, again, writing this in expanded form, each of these 3x's is really just 3 times x. So we have 5 copies of the 3, so we get 3 to the exponent 5. 5 copies of the x to the exponent 5. Okay, so reordering them here, you can see that a bit more clearly. You end up with 3 to the 5x to the 5. So we can distribute the x essentially to the 3 and to the x to get straight down to here. Okay, and then to take the same idea but apply it to a fraction, so let's say we have 2/3 to the exponent 5. Well, remember this just gives us 5 copies of 2/3. Okay, so 2/3 times itself 5 times. So putting that together, we have 5 2's, 5 3's, so we can write it as 2 to the 5 over 3 to the 5. So what you can see here is that 5 distributes to both the numerator and the denominator of the fraction. Okay, so these are all the rules that you would have seen back in grade 9. Okay, so where are we? There we are. Okay, so now let's actually try and extend these a bit further and look at some new rules for the grade 11 course. So we're going to go back and take a look at the tables that we did at the very start of this lesson and see if we can figure out some new rules. So something to the power 0, so x to the power 0. Let's go back to our charts here in our tables of values. Whenever we had an exponent of 0, you can see in the tables that we got, for all of these, a value of 1. Okay, so what this seems to suggest is that anything to the exponent 0 is 1. Okay, so is this actually true? Well, we have a rule here that says it's true. Okay, so you can sort of see here, it's anything x to 0 being 1, but let's just see if this is actually true. So for example, I'm going to take a look at the case where we have 5 to the exponent 5 divided by 5 to the exponent 5. So ignoring exponent laws for now, if I were to write this in expanded form, okay, rewriting it as division, this is really 5 copies of 5 divided by 5 copies of 5. Okay, so what happens here is all these 5's cancel, okay, and you're left with really just 1. Okay, which kind of makes sense here because you're dividing something by itself, so anything divided by itself is 1. But back in grade 9 we saw this exponent law that tells us if we're dividing powers of the same base, we can just subtract the exponents. We can rewrite this as 5 to the exponent of 5 minus 5, which is 5 to the 0. So what this seems to suggest here is that 5 to the exponent 0 is equal to 1. Okay, because we evaluated this using 2 different ways. One way we got 5 to the 0, one way we got 1. So you can probably see this being true for anything where you're dividing something by itself. So this is the reason why we have anything to the power 0 being 1. Okay, so that's a new rule for us. Okay, and next we're going to take a look at the idea of a negative exponent. So let's again go back to our tables here. So look at the cases here where we have negative exponents. Let's say we look at 2 to the exponent negative 3, we get 1 over 8. Well, does the value here that you see in the denominator, you'll see that all of our negative exponents had 1s in the numerator. Does the value in the denominator look familiar? And you might be able to see it elsewhere in the table as being the same value that we had here for 2 to the power of exponent positive 3. So if 2 to the 3 is 8, 2 to the negative 3 is 1 over 8. Well, is that true for a bunch of other ones? Well, let's take a look over here. If you look here, 3 to the negative 2 is 1 over 9. 3 squared is 9. Okay, so it seems to suggest here that if you're looking at these patterns, that there is a connection here. Okay, and you can sort of see it here for -3, 2, and 1. Okay, what this seems to suggest here is that, if I go back to these new rules here, is that x to the negative n is the same thing as the reciprocal, so 1 over x to the power of positive n. Okay, and let's start look at why that might be true. So let's look at the case here, this is in your notes, of 5 to the 5 divided by 5 to the 7. So we're going to do the same thing we do with the 0 exponent. Look at this in expanded form. So rewriting it as division with a fraction, we have 5 5's in the numerator, 7 5's in the denominator. When we cancel here, maybe you can see right now what we're going to be left with. We're going to be left with nothing in the numerator except 1. Okay, and the denominator we have these 2 5's. So this simplifies into 1 over 5 times 5, which is 1 over 5 squared. Okay, in our exponent laws, using the division rule, we'd subtract the exponents. We'd have 5 to the exponent of 5 minus 7, which becomes 5 to the negative 2. So that means 5 to the negative 2 and 1 over 5 squared are actually the same. Okay, so if you ever want to evaluate a negative exponent, okay, we can write it as a positive exponent. We take the reciprocal of what our base is. So let's just say we had 5 to the exponent negative 2. We could rewrite that as 1 over 5 squared, which would be 1 over 25. Okay, so now let's take a look at the case where we have fractions, and for this we're going to go back all the way to this last table, and maybe you can sort of see the same idea of the reciprocal happening here. So if you look at when the exponent's -3 and our value is 27 over 8, we'll look at the value of when it's +3. It's 8 over 27. So these are reciprocals of each other. And you can see that pattern continuing with the other values here too. So when the exponent's -2, it's reciprocal of when the exponent is +2, and ditto for when it's 1 and -1. So you can sort of see that connection there. So going back over here, we can safely say that, again, if you have a negative exponent, you can take the reciprocal of your base here and now change the exponent to being positive. So let's say we want to take a look at 3/4 all to the -2. Well, we could rewrite this as 4 over 3, so taking the reciprocal of the base here and then to the +2. Okay, so what we can then do now, using our grade 9 rules, distribute this exponent of 2 to both the numerator and the denominator. So we get 4 squared over 3 squared, which we can say is going to be 16 over 9. Okay, so these are some new rules now that we can use now in grade 11 to deal with negative and 0 exponents. Okay, so we're going to use these a lot coming up. Just some other things to remind ourselves of. A common mistake that we see all the time, and you probably did this a few times in grade 10 by accident, is if you have two things added together, to an exponent, you can't just distribute the exponent through to both values that are in there. So, for example, let's just say I give you x plus 2 squared. Okay, this is not going to be the same thing as x squared plus 4. Okay, this is absolutely, completely not true. If you want to do x plus 2 squared, you try and expand it and simplify it using an array. So we'd have x plus 2, which we know simplifies into x squared. We get 2x and 2x and 4. So we actually end up with x squared plus 4x plus 4. Okay, so it would be a missing term if we tried to do it this way. So never do that. In fact, in general, x plus y all squared is x squared plus 2xy plus y squared. So again, do not make this mistake. The other thing that comes up a lot is if you look at these two, these have a very subtle difference you see with the brackets, but it makes a big difference overall. In the one on the right, the negative is part of the exponent. So this is actually -3 squared, which is -3 times -3, which gives us +9. In the first one over here, the negative is not part of the exponent, only the 3 is. Okay, so it's actually 3 that's being squared. If you want to follow BEDMAS, you do the exponents. So you do 3 squared first, so 3 times 3 gives you 9, and then bring the negative in. Okay, so that's really just going over a lot of the rules, and we're going to actually start applying them in part 2.